Assalamualaikum everyone, I'm MD Jaman and this is my DLC final term presentation. I'm working with two other people and we're a group of three members including me. Our presentation topic is irregular sequence counter. We will be counting a specific sequence with a irregular sequence counter and show you how it will count the sequence. There will be simulations as well. So to start with, uh, we will show you what a counter is. So a counter is a device which stores the number of times a particular event processes as occur, often in a relationship to a clock. The most common type is a sequential digital logic circuit with an input line called the clock and multiple output lines. So what is irregular sequence counter? So a irregular sequence counter is a synchronous counter where the desired sequence can be displayed by a hex decimal counter in a sequence which might be as arbitrary sequence where the numbers aren't the one after another. There are many types of uses of a irregular sequence counter such as micro ovens, washing machines, frequency counters, digital clocks, analog to digital count converters, digital um, and digital wave generator, etc. So these are the 5 steps we will be using for to count the counter. Firstly, we will develop a state diagram. Secondly, with that help of a with the help of that state diagram, we will develop a state table. Later on, we will create a flip-flop transaction table, and then we will use K-map to derive the logic requirements, and lastly we will implement the counter process implement a counter process. So this is we the so with inner counter we will use D flip-flop, and this is the truth table of D flip-flop, and this is a state diagram and truth table of the counter. So here we can see our counter will be counting 5, then 3, then 6, then 7, then 2, and later on it will back again, so start with 5. Here we use the binary equivalent of these digits in this truth table, and here the counter will be counting the digits sequentially. Later on, how the counter works and the circuit diagram, those will be discussed by other two members.
Hello sir, my name is Shah Mohammad Fahim. My ID is 20439742. I am discussing about the K-map and truth table of irregular sequential counter. The numbers of irregular numbers are 5, 3, 6, 7, 2. First we take 5. 5's binary number are 101, then 3, 0, 1, 1, then 6, 1, 1, 0, then 7, 1, 1, 1, then 2, 0, 1, 0. Then again it's work like round and round, like start with 5, end with 2, then again start with 5. The irregular counter, then we take the truth table has 3 parts: present state, next state, and input state. The present states are q2, q1, and q0, and the next states are q2 plus, and then q1 plus, and q0 plus, and the inputs are d2, d1, and d0. Now we start with that. First we take present states. Present states are the irregular counters 5, 3, 6, 2, 1. First we take 0, 1, 0. This is 2, and then 0, 1, 1. This is 3, and 1, 0, 1. This is 5, and then 1, 1, 0, 6, 1, 1, 1. This is 7. Then we go to the next state like works. We take it like serial by serial, maintain with serial by serial. Then like first we take 101, this is 5. Then we take 1106. Then we take 011, this is 3. And then 1117 and 010, this is 2. Then we take the inputs comes from the d flip-flop table. D flip-flop tables are always constant, like 0 0 is always 0, 0 1 is always 1, then 1 0 is always 0, 1 1 1. And then we like present state and next state combine it with d flip-flop table, like q2 0, q2 has 0, and q2 plus next state has 1 0 1. We got d flip flop 0 1 is equal to 1. That's why d2 inputs we take 1. Then 0 0 and q2 parent state q2 0, next state q1 q2 is equal to 1, and 0 1 is equal to 1. We got 1. Then 1 1 0, 1 0 is equal to 0. Then 1 1 is equal to 1, 1 0 1 1 1 0 is 0. Then we go to q2 parent state q2 and next state q2, sorry, parent state q1 and next state q1 plus. Then again it works like previous one. 1 0 is equal to 0, 1 1 is equal to 1, 0 1 is equal to 0, 1 1 is equal to 1, 1 0 is equal to 1. It's come to d flip flop table. Then we go to q naught and q naught and q naught plus. Q naught is equal to 0 1, 0 1 is equal to 1, 1 0 is equal to 0, 1 0 is equal to 1, 0 1 is equal to 1, 1 1 1 0 is equal to 0. Then it works like d flip flop truth table, come from d flip flop truth table, it's constant. Then we go to the next slide. Next slide was the complete truth table. This is the complete truth table of the irregular sequential counter. The complete truth table likes present states, next states, and inputs present states are q2, q1, q0, and next state as q2 plus, q1 plus, q0 plus, and inputs are d2, d1, d0. And we again write q2, q1, and q naught 0 0 0 or 0 to 7 binary number, 0 0 0 3 bit 0 to 7 binary number, 0 0 0 1 0 0 0 0 0 0 0 1 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. This is 0 to 7 binary complete truth table numbers. Then we go to next state. In this irregular sequence we do not got 0, that's why it's like don't care. Its inputs are don't care, next states are don't care. 0 0 1 it's 2, 1 ones are not include this sequential counter, that's why it's also don't care. 2 0 1 0, 2 is included on the sequential counter, that's why its inputs and next states are written here. Then 3 also included, that's why it's also written. And 4 are not in the sequential counter, that's why it's also don't care. 5 are included, that's why it's written. 6 also written, 7 also written. Then the complete truth table was done. Then we go to the next slide, k-map. K-map also take on the truth table. In k-map like q2, q0, q1, d flip flop z, d2, d1, d0, d2. In this d2 we saw 0 0 column and row. Columns are 0 0 0 1 1 1 1 0, rows are 0 1. And then we saw so the when it cross it means don't care. One and the K maps also make when it's in groups 2 or 4 or 8. In this fast D flip flop, D2 we saw that there was a one group and two groups. First groups is 0 0 0 1 1 1 1 0 and 0. Q2 is 0 and Q1 Q2 is 0 0 0 1 1 1 0 0. And the next group was 0 0 and Q2 is 0 1 and 1 0 and which is and 0 1. It was make to fold, then it was group in four groups. Then we got D2, Q2 bar and Q0 bar. Then we go to D1. D1 we got same things. We got two groups like 0 1 and 0 1 1 1 and 1 0 1, and then 0 0 0 1 1 1 1 0 and Q2 is 1. That's why D1 is Q2 plus D0 D naught. Then we go to the next D flip flop, K map D0. D0 is D0 looks like D2 flip flop, K map. D2 is Q1 and Q0 is upper and Q2 is down. Then the column we saw the same two groups. Then one is four groups, and then we fold the two side and match. Then we take the four groups, four numbers, then this is the also group, and we got D0 Q3 bar and Q0 bar. This is the flip flop of irregular sequential counter K map.
Hi, my name is Jahidul Islam Roma and my ID is 194085552. As the rest of the members have covered the other topics, I'm going to cover the simulation of the circuit and the conclusion part. Here you can see the simulation of our topic. Here we have used three flip-flops, and on the output screen you can see the irregular sequence. This is the conclusion part. By using the equations from K-map, we can make this circuit properly. This moreover likely to be a countdown circuit 53672, which was seen in the simulation. So steps were followed properly and implemented successfully. Thank you so much. Here is the reference part where we have collected the data from these sites.